refreshes next door, and then allow the judges to have a look at. What you're going to be judged at are four criteria. It's based on your presentation, which is a quarter of it, the innovation or ingenuity of your design and how you've approached it, uh, on the function of it, whether it actually does the job you want to do, and the fourth criteria is the commercialization. So you really need to be able to address those four things. You have maximum of 30 minutes each team has. Take your time, make sure that you spread it so you do show the function of your robot as well as your presentation. We've had in the past sometimes teams who spend 28 minutes presenting and 2 minutes showing the robot. So I think you need to divide your time properly. We can't give you more than 30 minutes, but if you're shorter, that's fine. That doesn't get marked removed if you quick, but as long as you show your function well. So we will start with University of Toronto Robotics for Space Exploration. Are you guys ready? We are. Okay. Sorry? You have a video presentation? Oh. Do they want something to be able to show something on the slide? They need a clicker. He has our slides. Is there a clicker there?
before we go on, we just want to say who we are and who our team is. So really, our team was founded, Kareem and I founded Robotics for Space Exploration about a year ago at U of T because we were so excited and passionate about space, and we saw so much going on in the space industry now with SpaceX, Planetary Resources, doing NASA missions. We heard so much yesterday about the aerospace industry too. And the thing is, there's not really any program here for undergraduate students to kind of gain experience and prepare themselves for a career, exciting career in the space industry. But we really wanted to provide a space, no pun intended, for that. So, and actually, we think we've been successful already. After a year in operation, one of our team members is actually going to SpaceX to work in September, so that's really exciting news for us. But we operate out of the University of Toronto Institute for Aerospace Studies. So if you guys might be familiar with that, it's a great place to work. And Professor Tim Barfoot, Canada Research Chair in Robotics, Atomic Robotics, is our faculty advisor. So it's really a great honor to have him on board.
So let me tell you about what this is. This is Origin. It's our first attempt at making a rover that is designed from the ground up to be something that can assist astronauts on a manned mission to an extraterrestrial body. The Origin is designed to be a teleoperated rover that can operate at ranges of up to 2.5 kilometers, and it is something that an astronaut on an extraterrestrial body can use to perform tasks that would be ideal or not possible for the human to perform by themselves.
So what makes a rover like this useful in a collaborative effort on a manned mission to Mars? Basically, the rover needs to be able to do things that humans can't do and go places that humans can't go. And a big part of that is being able to traverse all sorts of unpredictable and hazardous terrain. Things like dirt, sand, rocks, boulders, different steepnesses of hills, all kinds of things. So we put a huge focus into building a very powerful drive system that's capable of handling all of these. So it started out, sorry, I don't want you to strain too much, but we started out with huge brainstorming amongst our teams. Followed that up with a lot of thorough research into what's already been done by leaders in the space industry. Once we understood what was going on here, we moved forward into building prototypes, testing different designs on rovers that fit in the palm of our hands, so we can really see what they do. We built all kinds of prototypes of different systems. From there, we built a motorized prototype. It's the exact same thing as this, but it's only this big. You can learn all kinds of different things about your system before you go into and invest into such a large project by making a small-scale version of it. And that's something we think is applicable to all areas of engineering design. Once we were happy with the prototyping, we moved forward into the computer modeling and design of the rover. And now that I've told you about the design process of what it took to build this drive system, I'll show it to you in action. So I'll just move it around. What's happening here is that the turning mechanism you see is something called skid steering, where you run one set of your wheels in one direction and the other in another direction. It allows you to turn on the spot even without radial design. Next, if Kareem drives the rover over my foot, basically what's happening is the suspension system is designed in a way that these can rock. And what this allows us to do is you can go over all kinds of shapes and objects like this while still maintaining a robust design. Kareem will talk to you about how the teleoperator.
So as Kareem mentioned already, our robot is a teleoperated robot. This is extremely valuable in space exploration because astronauts can be sitting in their base or in their lander and control the robot the distances up to 2.5 kilometers and explore safe areas before actually venturing into the danger that is space. And in order to achieve this teleoperation, we have an AV system on board, as you can see on this screen.
There's a camera mounted to the front. You can see. So we also have multiple view
viewpoints and multiple cameras on board that we can use to control the arm, to look at the back, and various settings. And in order to achieve this range for the teleoperation, we had to experiment with antenna design. And we ended up building our own antennas out of just coat hangers and pieces of wood, and experimenting with the range and the different antennas until we reached that optimal design. As you can see in that picture, we have a very long Yagi antenna that we designed from scratch, and we were able to get very long ranges, more than 2 kilometers.
So, a really important part of any manned mission to any planet, for example to Mars, is to understand the environment of such an extraterrestrial body. And so to understand the environment, often the environment isn't suitable for humans to habitat. So rovers such as Origin are sent out with a variety of onboard sensors. For example, a methane sensor, hydrogen sensor, carbon monoxide sensors. These are all sensors and gases that are important biological markers, as well as things like the ability to measure the moisture content in the air, the ability to collect samples and retrieve the soil moisture content out of them. All of these things are things that are built into Origin in order to allow it to perform tasks and understand the environment in a better way than humans can, and in a safer way than humans can. Also, what's important is once you identify an environment and an ideal site for collecting a more rich sample, for example, soil sample, Origin has the ability to collect that sample using the system and the arm that you see mounted on right now. When you think of excavation in general, what comes to mind? You think of a shovel or maybe a bulldozer. Essentially anything that with a scoop, right? And this is something that is a frame of mind that we have. But on here, what we've done is when you try using a shovel with a human body, it's very easy because we have so many degrees of freedom of operation. But when it comes to making it mechanically something that a robot does, it's not so simple anymore. So you have to think outside the box. And here what we've done is use a simple 5/16 drill bit. And all the drill bit does is it excavates. When you put it into soil and drill down, it pulls out a soil sample in the proper topological order that it is underneath the soil surface, which is often extremely valuable. We don't want to drill the floor here, so we won't show that. Also, to make something like this functional, you have to give Origin an arm that is completely dexterous and powerful. In this case, what we've done is you see the sample collection claw that's mounted on right now, but this may not be ideal for everything. We have a whole array of other claws that we've designed, such as an actual gripper that can grip objects and rotate them. It can fit pipes together, open and close valves, things that would be ideal for servicing equipment. So giving it that dexterity and power was extremely important and useful. And as you see here, another important aspect is that we tried making Origin as budget friendly as possible. And to do that, we didn't want to use expensive worm gears in our motor that would provide us with holding torque. So what we've done here is implemented a software solution that can give us that holding torque whenever necessary. So we can actually increase the pulse width modulation on the motors and increase the holding torque without actually having to have that in the hardware itself.
How many degrees of freedom is that on?
So if we look at the degrees of freedom, it's a combination of a Cartesian and a spherical system. So you have 1 degree of freedom in the translational horizontal motion. You have 1 at the elbow, you have 1 at the shoulder, 1 at the elbow, 1 in the wrist, and then you can include, when you add the grip around, you have the ability to grip objects. So 1, 2, 3, 4, 5, 6, 7, 8, 9.
So we can show the
He's just going to play a video for us that shows concept of flying.
So there you go. As you can see in our CAD modeling, this is what we started off with. And that's the design of the claw that we don't have here today. But the claw was also made from scratch. It's essentially a gripper design with a linear actuator inside with a lead screw mechanism, actually, that can grip objects with very great strength because it's a lead screw mechanism.
Also, with that level of design on the computer, you can learn so much about what your rover is capable of before you even build a thing. Because it's really time-consuming and expensive to make something, realize it doesn't work, make it again. But by doing high-level design like that virtually, You can see exactly how things are going to fit together, what size you need to make things. So you make it right the first time. You save time, you save money, and you get a better product.
Right. And obviously we need a brain behind all of this. So we have a microcontroller running on board on the rover, and we have code running on our computer. So basically, when we're controlling this, as Kareem said, we can't see any of this, so we have to do this all over wireless link. It's not tethered or anything like that. So it's basically, we're running Python code on our computers that are sending the signals over, wireless serial connection, and we're receiving that and doing all that. So there's no autonomy built into it, but the brains behind the machine are really just a way to channel the signals into the appropriate subsystems on board. In the future, we might go with a much more complete system, like something with a built-in operating system, so that we can do a lot more, adding some autonomous features to assist with that operation. But that's definitely something we're looking into.
Also, something we think it's worth emphasizing is that every feature of this rover, every subsystem, every part, every piece of the circuit has been designed by us and built by us. So if the rover, which it did, drives over a cliff and the wire gets disconnected, because we put each wire, we know exactly what to reconnect. If a mechanical system isn't working the way we want, we've done the design such that we can modify it. So we see a real value to, making everything yourself. Every part of it is exactly what we want it to be, and that way we can achieve exactly what we're trying to achieve.
And the last point on that is that we spent a lot of time with rapid prototyping tools. So you might notice, and a lot of them are actually hidden, there are a lot of 3D printed parts on this. So, to test our ideas and actually implement some of them with the 3D printed parts, we use a 3D printer. So, for example, these that you can see is a piece at the front. So 3D printing is a great way to make custom couplings, make custom pieces, and build prototypes that fail fast, as you heard yesterday. And that was instrumental for us.
Basically, by making these, we're passing it around. This is the kind of motor coupling we tested. Because this material is not designed to be strong, but it's designed to be exactly what you want it to be and made fast. So we can test stuff, see where it's going to fail, how it's going to fail, so that when we make the actual thing, we can make it properly.
Gentlemen, we're going to be testing this out of a nice smooth parquet.
Okay.
Yeah, we'll get to that.
So we have a section where we'll discuss this in more. So now that we talked about the different subsystems on the rover, the arm and the drive system and all of it, we're going to talk a bit about the second aspect that we mentioned earlier in the presentation, which is improving this human-machine interface and relationship. So we're going to show a few experimental technologies that we were experimenting with. And the first one is going to be the lead motion, which is, you might have heard, is a small sensor which composed of a couple of cameras and infrared sensors. And it allows you to track your hands and fingers very accurate. So I'm going to give a quick demo here where I'm going to control the robot completely with my hands. And the reason why we looked into these kind of technologies is because we think that there's a lot of value in improving the intuitive nature of controlling robots and this relationship. We find that the traditional joystick can get a bit cumbersome in certain situations. So I'll quickly show you the lead motion here after I pull up the arm. So I want you guys to be able to see the visualizer, which shows, I'm not sure if can you hold it up? So on this, yeah. Okay. So on this visualizer, my hands will, yeah. So you can see here that my hands are being tracked by the sensor. And so if I move my hands up, oh, I then lost the script.
So basically what we're trying to achieve here is, everyone's used to the standard game control type of system with joysticks and buttons. But what if you could make, an arm on your rover while sitting on Earth, you're moving your arm and it's tracking it and doing the exact same thing on Mars, Like that way you can achieve a level of control that you really just can't with joysticks and buttons.
So as I raise my hand, I can control the rover by moving
test all sorts of different things once you have a machine like this built. You know, we started with the joystick control, but now you can throw on a different kind of control system and use it to test that out. And that makes it really valuable.
And other technologies we're actually looking into is EMG and EEG technologies, which are even more connected to our body, which are just using electrical signals from our muscles or directly from our brain, and allow further transparent control of the robotic technology.
So one of the things we also are really excited to tell you about is a system we came up with called Robo UI. So I'm sure a lot of you have heard about the Internet of Things, and what we wanted to do is make our rover connect our rover to the internet, pretty much, so that while we build this tool, we can create it open source so that anyone can use it, and it's a really simple way for, you don't need a leap motion, you don't need a joystick. You can just plug in your telemetry into your computer, open up your browser, and start controlling your rover. So it makes it really simple. If I can just get the telemetry module, we'll show you. So we have a screenshot. If you can switch to the next slide, because unfortunately,
Yeah, there it is. Basically, this is a robot control interface that we created, and it's also an open source project. So basically, by downloading this, you can control the rover from anywhere. Somebody sitting in Brazil watching the World Cup could be controlling our rover at the same time.
So right now, it's important to note that this is being done completely through a web interface using, we've made the UI using HTML5 and CSS and stuff like that, and there's backend scripts running on the laptop which are controlling the rover through the telemetry module. So it's important to note, like Akash said, that we could literally be anywhere in the world as long as something like this is connected to the internet. It would be a great platform for people to experiment and people to actually use such a UI without having to do all the hard work that we've already done making something like this.
So now we're going to dive into the commercialization aspect and the testing and all that has gone on behind the scenes, and we're excited to play about that.
So, we all love robotics. We think it's really cool. I'm sure all of us are really excited by space exploration. But oftentimes, these things take a whole load of funding. And the people with the money aren't in it just for the joy of exploration and discovery. They want to see some money in it too. So that's why it's really important for us as engineers to understand the commercialization of this too. And first and foremost, this is meant to be an assistive device for manned missions to extraterrestrial planets. So anytime there is a space mission, there's a whole load of money that goes into that. So the one main focus area for such technology would be to use on such missions. But something that history has also shown us is that if something works in space, there's a good chance you can make it work on Earth too. So a lot of the technologies developed for space travel in the space programs have made huge impact here on Earth. And a technology like this can do the same thing. For example, something like this is really useful in like a search and rescue mission. Oftentimes places in the world are hit by natural disasters like earthquakes and tsunamis, and people get trapped under collapsed buildings, things like that. And it's really dangerous to send other people in to try to rescue them. At the same time, it's pretty difficult to make something like that purely a robotic mission, because every situation is different, every place is different. That's where we see the value of the human-robot collaboration, Send in a rover like this first to explore where are the danger zones, where are people trapped, look for the signs, look for what you're looking for, but from a safe distance. And then once you have a better idea of what you're actually dealing with, you can send the humans in, and that way your rescue is much more effective. And there's more.
Also, rovers like Origin are designed to handle extreme climates. And extreme climates don't just exist on Mars, they exist even on Earth. There are so many places on Earth where the temperature is too hot, like in a desert, or too cold, for example, in the Antarctic. And a rover like this can be fitted with any type of wheel you would want to make it suitable for various types of terrain, making it suitable for exploring terrestrial environments in a wide array of settings, even on our own planet.
And finally, a big field that rovers like these will be useful are the research world. So at University of Toronto and throughout the country, we have researchers working on various topics in robotics, such as autonomous robotics, mobile robotics, and having a research test bed, having a robust research test bed such as Origin is extremely valuable to just experiment with different algorithms, experiment with different software, and run it on board. And currently on the market, there are so many robots such as these that are being sold for this very purpose, such as ClearPath Robotics, which is a Waterloo company, for orders of magnitude more than it cost us to make a simple version like this. And we think by experimenting and making this rover more robust, we can do this for a fraction of the cost.
Guys, you got 5 minutes and there people want to ask questions.
That's perfect.
You done?
We're almost there. Yeah. So now I'm going to talk a bit more about the testing side of Origin. So in order to test our rover, we went to Wenda Provincial Park, and we experimented with the different environments there, such as rocks and so harsh rock terrain, boulders, that sort of terrain, as well as sand terrain on the beach of the Wenda Park. But we also went to the deserts of Utah for the University of Rover Challenge, which is an international competition organized by the Mars Society, and consists of 5 different tasks, including the sample return, as we mentioned earlier. So we had to collect samples, return, and analyze them on site, as well as assist some astronauts and traverse some rough terrain. As you can see in this picture, this is taken in Utah. And URC was an incredible experience in which we stretched the limits of Origin, and we were able to demonstrate the robustness of our rover in the harshest of environment, which simulated Mars to a great extent.
Basically, we built Origin. We've tested it from everywhere from the safety of our lab to the deserts of Utah. And we believe that there's a real commercial value for a robot like this. But the commercialization aspect of this doesn't end with just what you see here. You know, because for this to be very useful, what we've done is in the design, everything is super modular, you know? If you want a smaller rover, you plug in smaller wheels with smaller chassis. If you want a bigger rover, you can switch to bigger wheels. Some researchers might want a drill bit attachment, others might want a claw. You can change the arm in whatever system you like. If you want the power of a polar arm, you implement this system. If you want the precision of a Cartesian arm, you switch to a different system. So basically what's happening here is you have a customizable platform that can suit any customer need.
So what we kind of want to end with is a thought, a question, and our perspective on all this. So the way our presentation started, we talked about human explorers and we talked about robotic explorers, and they've all made incredible contributions. And our thesis has been, and in our club, it has been, the interface, the way they come together, and we think that they can do so much more. I mean, there's a lot of value in humans exploring space. We heard David speak yesterday. He was inspired by the Apollo program. He wouldn't have gone into that industry if he hadn't seen humans go into space. I mean, there's so much more you can relate to. We wouldn't, humans going into space would solve so many problems, as he said yesterday. We would have to be self-sufficient. We would have to figure out ways, to make a closed-loop system on another planet, conserving energy, conserving, all our resources, and solving a lot of problems there that actually are plague us here on Earth. So the thought we want to leave you with, I suppose, is we see robots in our society coming in and doing all kinds of things. They're doing a lot of things that humans do a lot more cheaply, a lot more efficiently, and better in so many ways. And we really wonder, do we want to go so far as to make them our explorers too? Will they have the same impact on society, on humanity, if they are the ones who we send alone without humans to go out there? Will they make that same impact, and will that limit our ability to innovate, to discover, and go further as a species? And that
Excellent, thank you. I'm sorry you did not leave time for people to ask your questions, but if there's a quick question, you can, we can have 1 more minute. I can add, yes, Catherine.
So we're running lithium polymer batteries inside. Around 45 minutes to complete and start. So we have a system where we can add in batteries based on how much runtime we want. So we have up to 7 LiPo batteries with 4,000 milliamp hours each, and I can go up to 45 minutes to complete and start. We have something like this is like a drive system for sure right now with the surface area we have is not possible with the same power that we have. But for things like, for example, resetting the microcontroller in case of a flaw, that's stuff like that we've talked about and experimented with. So we would have a solar panel which would have some sort of a reserve power generation that could do essentially a power cycle on the electronics. So that's sort of the application we can use solar power.
Also, the kind of thing that's solar powered, like the Curiosity rover, it's designed for a totally different purpose. It only moves on the order of like an inch or two every day, as opposed to something like this, which would be complemented by human explorers, which who can then manage the power.
Okay, thank you very much, guys. Thank you. Okay, our next presenters are Command Center, Gloucester High School from Ottawa. You can set it up here, and you can have a desk here.
Hello. Hello. My name is Mohammed Hassan, and I'm here on behalf of Command Center to talk to you about the engineering aspect behind ARMO. Necessity is the mother of invention. Today, almost everything runs on artificial intelligence and machines. So imagine if there was this one invention that could revolutionize an industry, maximizing efficiency, profit, and mostly the safety of the user. An invention that can be perhaps used to perform precise surgeries for the security of the public or even for lunar missions. Well, look no further, because the best way to predict the future is to invent it. We here at Command Center proudly present to you ARMO, which is Latin for arm and is our little big invention. PowerPoint, please. So, what is ARMO? ARMO is a robotic arm mounted on a four-wheel drive robotic car. The main function of ARMO is the ability to control the mounted robotic arm wirelessly using the user's own hand movements and gestures. And all that from a mobile control station, which enables an easy and convenient way of controlling ARMO. Now I say easy because it allows the user to follow up on ARMO as it operates in the desired industry, if they want to. Because there's another option, because we have first-person viewing device, which receives transmitted live coverage from the camera on board of ARMO. So, Armo as is right now can be described as follows. Dimensions of 23 centimeters by 21 centimeters and by 16 centimeters, with an approximate robotic arm torque of 50 newtons per centimeter, and weighing in at about 6 pounds, we can already accomplish great things with Armo. We can transport an item from point A to point B with great ease and at moderate speeds. And this is all thanks to 4 major components of our robot. First of all, we have the body, and it's home to the motherboard and all the electrical parts and the power source. It is built out of compact plastic material, capable of supporting the massive Armo as well as medium-sized items carried by Armo's robotic arm. The body design was chosen due to its given strength and the given volume. Next up, we have the wheels and the driving system. And in this case, in our design, we supplied each wheel directly with its own power, therefore ensuring a better driving experience. And each wheel is built out of tough and compact plastic material, which will ensure that Armo can travel across tough surfaces with ease. Next up, we have the onboard camera, and it's a camera that can be controlled within 120 degrees range. And as you can see, it provides it shows you what Armo is basically seeing as it operates. And this image can be transmitted directly to the first-person viewing goggles worn by my colleague right over here, which say you can man Armo from great distances as if you were there. Last but not least, we have the robotic arm. It is built to imitate a human arm. Therefore, we've connected several sensors and motors on Armo to imitate the joints of a real human arm. That way, we can ensure precise movement done by the robotic arm. Also, as you can see, we have the grip on the end of the robotic arm, and it was designed and built for easy and convenient use. Therefore, you see the 2 tongs, just easy, convenient pickup and release. And they are controlled by measuring the change in distance from a calibrated position on the control station. Therefore, as the distance between your index finger and thumb decreases, the grip closes in, and as it increases, the grip would open up. So, PowerPoint, please. So we can already cover great things with Armo as is. But how about for the future? With the existing technology present, a stronger, more powerful build is within reach. For starters, the body of Armo can be greatly enhanced. A proportional increase in the dimensions of the body would allow for more sophisticated systems to be installed and existing ones to be upgraded. The body can also be constructed out of very tough material, like carbon fiber, fiberglass, or even silicon carbide, which would not only assure an increased physical protection, but the ability to support heavier items hauled by Armo, without the damage to the exoskeleton or the interior expensive and sophisticated systems installed. Also, such material can be aerodynamically designed so that as Armo operates in the desired field, it would prevent undesired lift forces and drag, and it will reduce drag at high speeds. For the driving mechanism, we can install caterpillar wheels, which are ideal for driving over all sorts of surfaces, including tough, uneven, sandy, muddy, you name it. Whatever the industry needs, the caterpillar wheels will satisfy. And we can even install a GM motor for higher power and even more torque. On the subject of space, we can also install newer functions. We can install all sorts of sensors that can detect, if say working in the mining industry, any explosive gases in the air, sensors that can detect if Armo's heating up, sensors that can detect basically anything you want. We can include night vision. We can add night vision to the camera so it can operate Armo with ease at night and see precisely everything. So basically, whatever we add, it can only make Armo better and stronger. You can't go wrong with adding upgrades. So next up is the control aspect of Armo. How can we improve that? It's already great, it's already convenient, but there's a wired glove-like contraption we believe would be a nice upgrade, since it would allow the user more freedom to operate the robotic arm. Since the user won't be confined to a little contraption on the control station, with a glove-like contraption with lots of sensors, the user can move about his environment freely and control the robotic arm at will with even more precision. We can even install more monitors we can have more monitors belonging to the control station, which can display relevant information about Armo, including load size, load weight, power consumption, and anything basically that the industry requires. So, we know what Armo is. We know how Armo can improve in the future, but how does Armo really work? Well, on the control station, the remote control, which is the main transmitter, would send out radio wave signals to Armo. And then Armo would intercept the radio waves by the receptors on the robot that have been installed. And then those radio waves are interpreted by the motherboard and internal circuits, and therefore start the corresponding motor that can drive Armo forwards, backwards, left, right, haul the camera within 120 degrees range, or even move the robotic arm up and down. However, I would like to add that the robotic arm works a bit differently. Since we have used sensors to help imitate the movements of a human arm, what the sensors basically do is calculate the change in X, Y, Z coordinates from the calibrated position on the mounted control mechanism. And so once that change is calculated, we send it as radio waves over to Armo, where it again intercepts them and interprets them directly to the robotic arm, therefore moving the arm about its environment as the user intends. We know, in short, that we have something special here. We know that Armo is a game changer, and it can be used in various industries. We have something that, we have a control, the robotic arm control is something very unique, and just adds this extra level of precision that programming or even stick shift controls do not have. I believe Armo is a welcoming upgrade to all sorts of industries. And as Jim Rohn once said, if you are not willing to risk the unusual, you'll have to settle for the ordinary. Thank you, and this is the engineering aspect of Armo.
Thank you guys, all done. Any questions? Oh, you done that? No.
All right, you're gonna have to go back.
Okay.
Sorry about
Give
that.
5 minutes for questions.
Sorry about the confusion there. All right then. Wow, that was a mouthful. Ladies and gentlemen, my name is Tizu Bukhari, and where is my slide? Oh, never mind. I'm the head of marketing at Command Center. I don't have a big nose, though. All right, let's talk about Armo and how it can make you, and even me, a lot of money. Construction. Oh, God, construction. Construction helped Canada in the past, and it continues to do so today. To innovate, advance, and move on to the future, one must look at the past, said a great, wonderful man. That wonderful, great, humble man was me. In the 20s, the times were great. Everyone was getting that new car, that new home, that new great gizmo. But then the depression of the 30s hit. Everything was horrible. Thousands lost their jobs. What brought Canada back to her feet? Construction with relief camps. Even though it did fail, thanks to Bennett, not willing to give any money, construction did help. So, let's skip about 8 decades. What do you see? you see me at a bus stop observing a construction site. So what do I see, you ask? Well, you didn't ask, but anyways. What do I see? I see a crane operator trying to dig up some sort of underground wires, or I'm not sure what it was. And around him, there are 5 guys telling him where the overhead wires are, where the traffic is, how not to dig too deep or to dig deeper. 5 guys? That's pathetic. With ARMO, you only need 1, because with our mobile command center, with our mobile control station, you can simply walk around. Oh yeah, that's how deep I need to dig, instead of being in that crane. So on average, PayScale reports that you're paying anywhere between $17 to $50 an hour for each of these guys. That's over $4,500 a week for 5 guys standing around. Oh God, it's way too high. But with 1 operator, you simply need to pay him $22 an hour, which is around $50,000 a year, instead of the $250,000. While this operator is moving around, he will be the only one in the danger zone, per se. So he can avoid that 806 national deaths every year in construction site accidents. And guess what the main causes are here? Struck by an object or caught in between. 8. All right. Now that we know that there are a lot of accidents on construction sites because people don't know what they're doing, with ARMO, you do not need that, because 1 operator knows what he's doing instead of having 5 guys. Not only are you saving on cost, but you're saving on human fatalities, human life. Other effects of staying on construction site include COPD, which we all know, is chronic obstructive pulmonary disease, asthma, lung cancer, and silicosis. Okay, all right. As you can see on the picture on my left, that is an American penny. Beside that is 1 bit of silica dust. That's the maximum you're allowed in 1 day to be safe, like to protect your cardiovascular system, essentially. But look right to the next picture. The construction worker is not wearing any sort of mask. I'm pretty sure that's way past the daily amount that you're allowed. Every year, silica dust causes an estimated 500 deaths. But how can it all be avoided? With ARMO. With ARMO, the construction worker does not need to be on site necessarily. He can be even, 2,000 miles away, because with the control system and the camera, he can see what he's doing while being safe. Speaking of toxins, because we are there anyways, with ARMO, you can attach IR sensors, chemo sensors, radiation sensors to detect any sort of toxins or any chance of toxins. Oh. Mining. Oh God. Mining is one of my favorite industries in Canada. It is also 6.4% of our total economy. That is $29 billion. Wow, that is a lot of money. With ARMO, that figure can go much, much higher with fewer costs, because ARMO can go deeper in higher temperatures, lower temperatures, higher pH levels, lower pH levels, higher pressures, lower pressures, because ARMO is a simple robot. It does not need to withstand it does not need the conditions that human body needs to function properly. And at the end of the day, all you need to switch the operator instead of bring the miner back up and send another one in. On average, in Canada, miners are paid $92,000 a year. But that number, in places like Perth, Australia, can go up to $200,000. A light machine operator, however, someone that could possibly operate ARMO, only gets paid $45,000. You're saving you're saving more than 50% of your costs, not to mention food, travel, health, and living in the actual mines up north. As with accidents, in the US alone, mining accidents went down from 1,500 a year to 35. But 35? Can you imagine someone telling you that you lost someone really close to you because you love your iPhone 99Z too much? With ARMO, we can avoid that completely, because miners do not need to be in the mine. They will be safe from all types of accidents. Worst case scenario, ARMO gets destroyed. Did we lose a life? No, we did not. Now, these are just accidents. It is estimated that 24,000 people die from premature death from mining. How is that, you ask? Well, in mining, we all know that we're exposed to a lot of toxins, and most of these people, on average, lose 14 years of life. That's 14 years of boring recitals that we all love, even though we hate them, boring baseball games that we could have gotten while saving more than 50% of our total costs. Another 38,200 people die because of soot pollution, caused mainly in coal mining. Other health includes COPD, cancer, heart disease, and the mercury in coal mining causes loss of intellectual power. So, how can we avoid all these risks? Once again, with ARMO, ARMO can go into the mine. It does not need a human operator in the mine while it's functioning. A human operator can be, once again, 2,000 miles away, safely tucked in some sort of container, working, while ARMO is actually in the mine, being exposed to all these toxins. As I have bombarded you with medical facts, it's time to do so more. The US Army is currently introducing telemedicine robots, like the ones you see up there. Now, these robots are great. These are used to assist medics in combat to perform emergency procedures like trepanning. But however, these are great, but they're not it. These robots are not the same thing as a surgeon operating himself or herself. Currently, surgeons use joysticks like the ones you can see in the pictures there to control minimally invasive procedures and microscopic surgeries. However, with Ethicon Endosurgery's latest tools, we can simply attach those tools to ARMO itself to make the surgeon part of the tool, or the tool part of the surgeon, rather than two complex beings put together. This will also save you thousands of dollars in travel costs and the inconvenience of the surgeon themselves, as they can be, once again, thousands of miles away from the patient themselves. ARMO will also save a lot more time in the golden hour. Heck, it can even make the golden hour the golden 15 minutes. That's the best time you can give to the patient after initial emergency symptoms. Oh God, nervous much? All right, after initial emergency symptoms like a bullet wound to the head, the golden hour really helps us because it can give the patient the best chance of recovery possible. But with ARMO, why have a golden hour when you can have a golden 10 minutes? Now, that is a huge problem. Now, as I said, the answer to the golden hour problem is ARMO. Another problem we're having, I'm really bad with these, is that the Canadarm is not reaching its full potential. Why is it that you ask? Although with accurate computers and joysticks, it can reach accuracy. But accuracy and precision are two different things. Precision can only be reached with humans and their instinctive feel for it. Because with ARMO, we give you the control station to give you full power with your own arm. So Canadarm would be your arm, rather than a set of points or joystick. Now, what else is the ARMO really designed for? Mars. We all know that Buzz Landorf's upcoming mission to Mars. If we don't know it, it's basically where he intends on permanently shifting humans to Mars for further discovery, mining, and to start a new colony on Mars. So how would ARMO assist there? With ARMO, instead of getting all those oxygen tanks and those suits to walk outside to do any external repairs or to even do more discoveries and do stuff that the rovers cannot do, ARMO can simply be going out there. It's a machine. It does not need oxygen to live because it does not live, period. So you can do all these external repairs and such and still leave ARMO outside for thousands and thousands of days even, potentially. So, in conclusion, what do we have? In conclusion, ARMO is the future. Embrace the future, because ARMO is it. Ladies and gentlemen, Command Center, out. Any questions?
Okay, thank Thank you very much. Questions? We have a few minutes. Mr. Wolzak?
No, I don't need that. Apart from wondering how you're going to keep the 300,000 people you just put out of work off welfare. Things going. Are you considering a larger prototype?
Of course, but we're considering all, because right now we wanted to save on cost, so we built a very small prototype. But Armo can be even bigger or smaller according to your needs. It's not that Armo's one definitive sign. It can be for, let's say for surgery, you would need to make it much smaller. But for mining, you could make it much, much bigger.
How much did it cost you to make this one?
All right, at a command center, we're always trying to save budget, trying to save you money and trying to save us money. So total this year, it cost us around $500 to $600 to build this prototype,
Including
including everything.
Very good. And there are how many motors operating on that rover?
There are 4 motors individual power.
For the wheels, but and then you have a couple of motors for the arms?
That's for the servo motors.
Yeah, yeah. And the camera has a motor too?
Cameras X and Y axis, which is 2 servos, one is goes on the next.
Okay. All right, very good. And the battery is rechargeable batteries, though?
It's rechargeable electric polymer battery.
Very good. Any other questions for anybody else? Great, thank you very much, guys. Well done. Okay, next we have a series of robots which are designed to compete in a specific competition which requires certain throwing of balls, and we're going to look at them with their capability and what they think those lessons have taught them. First, we start with 4618 CN Robotics from Cardinal Newman Catholic Secondary School in Hamilton. Guys, the floor is yours. What? What?
You ready, Martin? Hi, my name is Matthew Payton. I belong to Team 4618 CN Robotics. I'm here today with Martin, Christina, Philip, and Christian. At Team 4618, we obviously compete in the FIRST Robotics competition. We compete hard, we do our best, and every year we manage to put out an excellent robot. But what we like to think that sets us apart from the other teams is not only do we build the robot to compete in the competition, we like to see what else our robot can do. And what we've come up with is, we think our robot Dusty can easily be put right into the warehouse situation. Everyone knows, in large companies such as Amazon, they take thousands of workers and all